Hello and welcome to this video on one of the weird things about water. Why does water freeze faster if it is hot? This is a phenomenon known as the Mpemba effect. Most people know that the more solids in a liquid, like water, the faster it freezes. They also know that adding alcohol makes it freeze less readily. What is not known as widely is that freezing hot water becomes a solid more quickly than cold water. That last statement seems to fly in the face of any logic. Let's look at water in general first. It's a liquid between 0 degrees Celsius and 99 degrees Celsius. From 100 degrees Celsius onwards, it vaporizes and becomes a gas. It is a solid below 0 degrees Celsius. These three temperatures are important points of reference. These are worth keeping in mind because the Mpemba effect does not always apply, which is yet another mystery. Theories for why it happens have included that heating the water causes evaporation, which reduces the volume of water to freeze, that there's a frost layer on cold water which insulates it, that different waters have different concentrations of solutes, which can then be altered by the heating process. When looking at this empirically, researchers found that water will freeze at different temperatures, largely due to mixes of impurities. When you take two samples that should be the same, warm one to room temperature and one to 80 degrees centigrade, and freeze them. If there is an existing difference, this difference will continue to be demonstrated despite the Mpemba effect, which means it doesn't occur properly. It will always be a case that the highest freezing point always freezes first. It doesn't matter if you heat it and then freeze it. This lets us figure out which will freeze faster, and why the Mpemba effect does not always apply, but it does not explain what is causing the effect. Causality being somewhat more important than predicting when it will happen. The Mpemba effect and the underlying mechanism by which it occurs has eluded us since 400 BC, 2,400 years, and we still didn't know what was happening. That is how long it has taken us to have a strong model to explain the Mpemba effect, but this method, so to speak, or explanation is by no means definitive. It is possible, based on the current front-running theory, that it all comes down to hydrogen bonds. Hydrogen bonds are a funny thing. They like to help water connect. Adding an extra hydrogen to a water molecule creates heavy water. And of course, in solution, water will always be changing between a mixture of heavy water and regular water and water without the hydrogen. This means that there are three states it's in, and it will vary, but it spends most of its time in the better known dihydrogen monoxide state. When you heat the water, you find that the hydrogens stretch out and away from the oxygen. This interferes with the natural repulsion between molecules that are caused by the covalent bonds between the oxygen and the hydrogen. This means that they begin to store energy. This is what the heat imparts: energy. While you warm it up and these hydrogen bonds stretch out and further apart, this energy becomes more. But in order to come close together and cool down, they need to give up this energy. This is the process by which you can heat and cool substances. That doesn't sound like anything very important until you look at what is happening when you have both these covalent bonds with the hydrogen and what the introduction or removal of energy does. The process of removing the energy from the excited water molecules that have been warmed up occurs faster than what it does in cold water. That is both a product of normal cooling, movement of heat from high concentrations to low concentrations, and the hydrogen bonds. That appears to be what is happening with the Mpemba effect. A combination of both the normal thermodynamics and the effect different elements have on the molecule overall, and the way it can both gain and lose energy. In order to explore and somewhat proof this theory that already fit into the wider body of knowledge and seemed to make sense, further testing was needed. And this further testing looked at water molecules and the strength of hydrogen bonds, specifically how they change in relationship to other water molecules in the vicinity of one molecule given changes in temperature. What they found was that as the temperature rose, the bonds became weaker, eventually breaking. These fragments, so to speak, could then reform, realign, and create a crystalline structure. This is a solid, and the solid version of water is ice. These acted as nucleation points, and that kick-started the freezing process. This found that when you took cold water, breaking these bonds was nowhere near as easy. Remember, bonds that were stretched out because they became excited with that extra energy being introduced in the form of rising temperature. When you have cold water, the weaker hydrogen bonds will take more to break, and that means more time has to pass and more energy has to be lost. In order for that to happen, you simply have more time being applied. This is one reason why, if you have a very high temperature by comparison, the number of hydrogen bonds that will break is far higher than those at a lower temperature. Although there is no definitive explanation or accepted reason behind the member effect, the broad evidence suggests that it's simply a corresponding effect to a significant rise in temperature, leading to excitation in the bonds between the elements in a molecule, primarily the hydrogens and the bonds they have, which makes it easier to form a new substance, or at least the crystallization process required to make a new substance like ice. Think about the way that diamonds can be formed by high pressure and high heat. It's because you force the carbon into the matrix needed to form the crystal. In the same way, the member effect is effectively exhibiting the same phenomena, but in the case of water turning into ice. Research does generally show that the degree, or at least difference in effect it has between cold and hot water, increases exponentially based on the temperature at which you begin the freezing process. That meaning something at a very low temperature and something at a very high temperature will find the high temperature item freezes much faster, and that this difference will increase the hotter the second sample gets. This theory has been tested and somewhat proofed in other systems. One particular example using glass beads in lieu of water, as it's hard to study water specifically, as you can rarely isolate single molecules, if at all. What you can do is take the glass bead and put them into an environment that simulates the same scenario. You can also repeat this experiment a large number of times, collecting a large amount of data. That significantly improves the strength of any experiment. These models have found the same fundamental process as what we see with water under the hydrogen bond theory. That is, the hotter something is, the faster it will lose its temperature and become a solid. That's how the member effect works. Beginning 2,500 years ago, being typified by the apocryphal tale of watching hot ice cream solidify faster than cold ice cream, and now multiple physicists looking at this in different ways, trying to create a model to understand exactly what is happening in one of the world's weirdest chemicals, water. Thank you for watching this video. If you have found it interesting, consider liking, sharing, and subscribing. Please post any comments, questions, or suggestions that you have below.